Swayam Prabha. Digital India. Educated India.
I welcome you all to the session of Thermal Engineering Basic and Applied. Today we shall try to derive the expression of mass flow rate of fuel through the carburetor. In the last class we have discussed about the simple float type carburetor and we could establish the expression of the mass flow rate of air. For a simple float type carburetor, though we had the expression of the mass flow rate of air, we also need to calculate the mass flow rate of fuel and then we can figure out the fuel air ratio, which is important for the operation of the internal combustion engine, particularly for the SI engine, because this particular element is essential for the operation of spark ignition engine. And then also we will try to discuss the limitations of the simple float type carburetor. And you know that the carburetor is simple float type. So, it may not be always possible to provide required air fuel mixture or fuel air mixture by using this carburetor to the engine at varying load, and we shall discuss those aspects even in today's class. So, you know that if we try to obtain the expression of the mass flow rate of fuel, we need to draw the simple float type carburetor again. So, if we try to draw the simple float type carburetor, say this is section, if I use, so this is the orifice and fuel discharging tube, and if we provide the venturi like this, because we had seen in the last class this venturi is provided only to have a pressure difference in the course of flow of air through the carburetor, and that pressure difference. So, if this is section AA, so this is section AA and air is coming, so this is clean air, okay. And we have this is two engine cylinder and we have one throttle valve here, and this is the float chamber, if this is the we have one float and that is connected like this. So, this is fuel supply, this is air vent and this is the float chamber. Now, this is the height difference delta H or simply H. So, we could establish the expression of the mass flow rate of air. So, today we shall try to have the expression of the flow rate of the fuel. So, now see, this is again open to atmosphere. So, if we try to, this is also atmospheric pressure acting on the fuel surface, and if we consider this is surface AA again. Okay. This is also atmospheric pressure of air, this is also the atmospheric pressure acting on the fuel surface, and this is this section we are considering AA, while this section is BB, this is BB. So, if we for the flow of fuel, if we write the equation between section A and section BB or section A prime, I am giving the name section A prime. So, that is we can write P A by rho f into G plus C A square by 2 G equal to P A by rho f into G plus C V square by 2 G plus H f plus this delta H. So, in this case this is, you can see this is the energy equation steady flow. Now, you have you are familiar with this equation because you have studied in fluid mechanics. This is modified form of the Bernoulli equation, because Bernoulli equation cannot be applied for the viscous fluid. So, this is valid for the inviscid incompressible, inviscid fluid incompressible, but here we can see that we are writing this modified with these two terms. So, now this is basically the height difference between the surface of the fuel in the float chamber and the float this orifice. So, this is orifice this is fuel discharging tube. So, this is fuel discharging tube and this is the orifice of the fuel discharging tube. So, if the difference between these two, that is the this orifice of the fuel discharging tube and this height of the fuel in the float chamber is delta H, then that is taken care in this equation. So, that this particular height difference is also very important, because what we had discussed in the last class, that we would like to have a drop in pressure of the air while it is flowing through this passage, and that pressure difference is responsible to have the flow of fuel from float chamber to this particular orifice point. Okay. So, while we are considering flow of fuel from float chamber to that particular point, that is orifice discharging fuel discharging point, we also need to take the static height difference. So, that particular static height difference is already taken care of while we are trying to establish the expression of mass flow rate of fuel, and this particular term is the frictional losses. Okay, or frictional loss. I mean, if we can write that this is the, we are writing frictional losses because you know that friction between the internal friction and external friction. So, internal friction is the friction between the fluid layers, while the external friction refers to the friction between solid wall and the adjacent liquid layer. So, this is frictional losses, and again if we see that the cross sectional area of the float chamber is much higher than the cross sectional area of the orifice point. So, we can write here that cross sectional area of float chamber is much greater than of orifice, and then we can consider CA is much less than CB, right, and then we can write that, and if you assume that flow of fluid or flow of fuel flow is considered to be an ideal fluid flow. If we assume, so this is the assumption, and then we can write, if this is the case, then we can, this HF is almost equal to 0, then we can write CB square by 2 from the previous equation. So, this is negligibly small, we are not going to consider this, we are assuming that the flow of fuel as an ideal fluid flow, and then we can write CB square is equal to PA minus PB, CB square by 2 is equal to rho f into G minus delta H. Therefore, we can write CB equal to under root PA minus PB by rho f minus rho f G into delta H multiplied by 2. So, this is the velocity of fuel at the orifice point, that is the at the discharging point. So, this is the fuel flow velocity at the orifice. So, that is orifice. So, now if we know the fuel flow velocity, then we can calculate the mass flow rate of fuel m dot f equal to density of fuel at section B, that is rho f, area of the orifice at section BB, that is AB, into CB. So, if we write, then we can write m dot f equal to AB, that is known, multiplied by rho f into 2 into PA minus PB divided by rho f minus G into delta H. So, that is the expression, right. So, if we take rho f inside the root, then we can write it, we can write this like this, under root twice into rho f into P A minus P B minus rho f square into G into H, or I can write rho f G into delta H. In that case, I can take this rho f out the bracket. So, this is the expression of the mass flow rate of fuel, but we had taken an important assumption is that we are going to consider the, or we have considered the flow of fuel to be an ideal fluid flow. That is not possible in reality. Also try to understand that while we have established the expression of mass flow rate of fuel, we also did not consider the effect of surface tension that would be there. Why it is important? Because if we try to go back to the schematic depiction, we can see that fuel will flow, this fuel will flow through a tube or a flow path which is very small. So, when the length scale of the fluidic pathway is reduced, the surface tension force will be an important force to be considered in the analysis, but we did not consider that. We have also ignored the frictional losses, that is both internal and external frictions, and surface tension force we did not consider. Accounting these factors, the expression that we have established here is not the actual mass flow rate of fuel that we are going to get, right. So, this is delta P. Try to understand, this is basically delta P. So, that is the pressure drop between section B B and section A prime. I am also writing that I have considered that pressure at section A prime and A is P A, that is atmospheric pressure in both sections. So, the pressure difference is important to have a flow of fuel from float chamber to that orifice or fuel discharging point, and that pressure difference is created by the flow of air, and that is why this venturi is provided. But the expression that we have obtained today is not the actual expression of the mass flow rate of fuel. Why? Let me tell you, because in reality, though here also we are going to consider that isentropic flow. In the last class, if we try to recall, we had assumed that the process is modeled by an isentropic process, but so long as the flow occurs through this particular configuration, and we can see that the flow area is reduced, and if the flow area is reduced, there will be several several losses. So, we cannot ignore all those losses trivially, and the isentropic flow behavior will not be the actual scenario. So, the mass flow rate of air that we had in the last class again was the actual mass flow rate, and that was the ideal mass flow rate, and to obtain the actual mass flow rate we had to multiply with discharge coefficient CDA. Similarly, today we have obtained the mass flow rate of fuel, and as we have discussed, accounting for the frictional losses, accounting for the surface tension effect that will be there, because fuel flow will be there through this small orifice, and also the specific gravity of the fuel. Accounting these three factors, actual mass flow rate of fuel should be less than the ideal mass flow rate that we have established in today's class. So, let me write here this mass flow rate is the ideal, right, and that means our analysis, that is the ideal fluid flow, will deviate in real practice accounting for these factors, that is the specific gravity of the fuel, surface tension effect as well as frictional losses, and hence the mass flow rate of fuel is obtained here is the ideal mass flow rate. So, that means if we write the actual mass flow rate of fuel, that would be, so actual mass flow rate of fuel m dot f actual would be equal to CDF into m dot fuel ideal. So, that means CDF, discharge coefficient of fuel, is m dot fuel actual by m dot fuel ideal, and this discharge coefficient varies from 0.94 to 0.99. Okay. So, this is for the high flow rate and this is for the low flow rate. And the coefficient, so that means this particular coefficient is responsible for the deviation of actual flow. So, basically you know what we had written, that frictional losses surface tension effect and fuel specific gravity. All these three factors are the responsible factors for the deviation of ideal flow, for the deviation of the flow which is there from float chamber to the orifice point from the ideal flow behavior. So, though we could establish the expression assuming the flow to be an ideal flow, but all these factors are responsible for the deviation of actual flow from the ideal one, and it is because of these factors this coefficient is defined and the value of this coefficient is varying from low flow rate to high flow rate, that is from 9.94 to 0.99. So, these are the factors responsible for the deviation of real flow from ideal flow, right. So, if we mark them, this is the case. Okay. So, now let me discuss an important point. So, what we could write, you know, that very important point. In the last class we had assumed that this is steady state steady flow. In fact, in today's class also we had written that you know energy equation that is even steady, that is not in its unsteady form. So, we are assuming that the flow, whether it is flow of air or flow of fuel from float chamber to the orifice point, flows are steady. So, you know that that means steady flow behavior, whether it would be a case in real applications or not, that we need to know. The flow will be steady if there are certain points, and if we can fulfill all those points while the flow is taking place, whether it is a flow of air or flow of fuel. You know that if that particular carburetor is responsible to supply air fuel mixture or fuel air mixture to a cylinder, and if the cylinder is single cylinder and 4 stroke, what we had seen in a 4 stroke single cylinder engine, we need to supply air fuel mixture only during intake stroke. Remaining 3 other strokes are the ideal stroke, and we do not require to supply air fuel mixture. So, that means it is a kind of periodic supply of air fuel mixture to the cylinder during the operation of the engine, and that periodic supply of air fuel mixture to a cylinder, and that is single cylinder 4 stroke engine, will make or will bring unsteadiness in the flow of air. If it is, if that particular aspect induces unsteadiness in the flow of air, the flow of fuel also will be unsteady. So, the assumptions that we had taken in the last class to arrive at the expression of the mass flow rate of air, that is steady state steady flow. So, this would be valid if we need to supply fuel air mixture using this simple flow type carburetor to multi cylinder engine, and if it is 2 stroke engine. So, the steady state steady flow assumption is more valid for the multi cylinder engine and 2 stroke engine. Why? For the multi cylinder engine, say we are having 4 cylinders, then if we design in such a way that when there is intake stroke, if the intake stroke in the first cylinder, remaining 3 cylinders are having or are executing different other strokes, and when intake stroke is over in the first cylinder, maybe second in the second cylinder intake stroke is started. So, what we can do? We can have a continuous supply, more or less a continuous supply of air fuel mixture from this carburetor to the engine cylinders, and that will lead to almost steady state steadiness of the air fuel mixture. That is what we can see. Also, if it is 2 stroke 2 stroke engine, we had seen that 4 stroke engine only one intake stroke, vis-a-vis there are 3 different other strokes. But for the 2 stroke engine, in one intake versus one other stroke. So, the periodic filling, even if it is a single cylinder engine, the time gap between 2 consecutive intake strokes is very less, and we also can approximate the flow of air to be almost steady. So, unsteadiness in the flow behavior will be there if a simple flow type carburetor is designed to supply fuel to a single cylinder engine and 4 stroke engines. Instead, if it is designed to supply air fuel mixture to multi cylinder engine and 2 stroke engine, the approximation steady state steady flow is more valid. That is what I wanted to discuss now. Okay. Now, I will be discussing one important point, that see, if we consider in the last class we had discussed, or we had assumed that the flow of air is kind of, there is no assumptions we had considered in the last class, that we had considered in the last class. So, basically no assumptions behind the flow of air that we had taken in the last class, except we had considered that frictional losses are negligibly small. But that and we had started our discussion from the steady flow, steady state steady flow equation. Instead of considering steady state steady flow equation, and we had also assumed that the process is modeled by an isentropic process. but if we assume that air to be an incompressible fluid, and if we write the equation between these two sections, if we write the equation between these two sections and you are assuming that air to be an incompressible fluid, we can write like this: air to be an incompressible. So, this is again we are assuming fluid, we are assuming then we can write Pa by rho equal to Pb by rho plus Cv square by 2g or 2g rho g. We are assuming that Ca is much less than Cb. That means velocity of air at section Bb, Cb would be equal to under root 2 into Pa minus Pb by rho, and this is rho of air. So, this is rho air. So, I am writing rho air and this is rho air, right. So, this is the velocity of air at section Bb, provided we considered the flow of air to be an incompressible fluid flow, right. Now, what we can see, say this is equation number 2, and if we go back to the previous slide and if we give this is equation number 1, if this is equation number 1, in this equation or say this is equation number 1b and this is equation number 1a. So, if we look at this equation number 1a, and if we assume that the delta H is almost 0. So, that means if we consider that this delta H is very small, then what we can assume that if we look at this expression, then Cb would be equal to 2 Pa minus Pb by rho f. So, we can write here we can write, right. So, for when delta H is very small, from equation 1a we can write Cb is equal to 2 into Pa minus Pb by rho f, right. So, this is equation number 3 say. So, this is equation number 3. So, what we can see? So, that means if delta H is very small, then the small pressure difference is needed. If delta H is very small, a very small pressure difference is needed for the flow of fuel from float chamber to the orifice point or discharging point, fuel discharging point. So, if the height, if we go back to the previous slide, if this delta H is very small, then a very small pressure difference is needed to have a flow of fuel from float chamber to the fuel discharging point. And if this is the case, and if we assume that air to be an ideal fluid, then the flow of air to be an ideal fluid flow, then we can see by looking at equation 2 vis-a-vis equation 3 that these two expressions are almost identical, except this is rho air and this is rho f. So, that means flow of fuel at section Bb and flow of air at section Bb, these two are constants, because we need to calculate mass flow rate of air. So, fuel air mixture, that is mass flow rate of fuel by mass flow rate of air. If it is actual or it may be actual. So, the mass flow rate of fuel by mass flow rate of air, this is almost constant and that depends on the pressure difference delta P. Okay. So, this is almost constant and depends on P A minus P B, right. So, this is P A minus P B because you can see that C B. So, this is velocity of air at section B B C B, this is also P A minus, that depends P A minus P B. So, higher the pressure drop, higher will be air velocity, and if higher the pressure drop, higher would be the velocity of fuel. So, this is velocity of fuel at section B B, right. So, if we, because our intention is to obtain the mass flow rate of fuel. So, this is multiplied by density of fuel and area of oil fuel discharging tube. So, area is constant, density is also constant, and so basically if C B is constant, mass flow rate of fuel is remaining constant, and that is function of P A minus P B. Similarly, mass flow rate of air at section A B B is area at section B B and the density of air at section B B, and this is the function. So, we can see that the mass flow rate of fuel and mass flow rate of air, the ratio is also constant and is a function of delta P, that is P A minus P B. So, you know that here we could write. So, basically this is the area of orifice at fuel discharging point. You should not be confused because A B we had used, that is the area of section B B, but today this A B is not the area of at section B B, but this is area of orifice at the discharging point. Okay. So, what we had seen that the mass flow rate of air and fuel is constant and that depends on P A minus P B, that is pressure drop. So, this is the pressure drop. Now, let us discuss one important point. Say we had discussed in one of the previous classes, that is the regimes of internal combustion engine operation, and we had seen that percentage area of the throttle opening. So, try to understand percentage area of the throttle opening means, so this is the pressure drop. Now, this is the atmospheric pressure that is acting over here. So, higher the pressure drop across the throttle valve, then we could establish that there are 3 different regimes. Okay. And say this is C, this is B, this is A, and this is D. Okay. So, this is power zone, this is cruising zone, and this is idling zone. Okay. And if we write it, so this is now P A minus P B delta P. So, higher the delta P, so basically cruising zone we need to supply higher the throttle opening area, that means we need to have higher delta P. So, higher the delta P or delta P. So, now if I use it, see we can see that this is the idling zone, we need, so this is fuel air ratio and this is fuel air stoichiometric. So, this is fuel air stoichiometric, right. If we increase the pressure difference, we can see that we need more amount of air fuel mixture. So, we are trying to move from idling zone to the cruising zone and the power zone. Now, if we use the simple float type carburetor, what we can see, we have expressed that mass flow rate of fuel, that is fuel air mixture, is almost constant, and it is a function of Pa minus Pb, and it is a linear function of delta P. So, if a simple float type carburetor is designed to supply adequate air fuel, and see this is if we say suppose it is designed from here, and this initial so this is initial pressure drop. This initial pressure drop is needed for the real application, because the fuel will not flow until and unless the driving force is sufficient to overcome the frictional effect as well as the effect that is there due to surface tension. So, this initial pressure drop is needed for the flow of fuel from float chamber to the fuel discharging point, because this pressure drop is needed to overcome the frictional losses as well as the effect that is there due to surface tension. So, if a simple float type carburetor is designed to supply air fuel mixture or fuel air mixture which is good enough for the idling zone, because it is a linear function of delta P, Pa minus Pb. So, if we increase Pa minus Pb, it will increase. So, suppose this is the case, this is case 1, and we are superimposing another one case, say a simple float type carburetor is designed to supply like this. So, this is 1, this is 2, and another case, if we draw here, say this is 3. See, if we consider these 3 different cases, what we can see is that that if a simple float type carburetor is designed to supply fuel air ratio for the idling zone. So, that means that if we design to supply fuel air ratio following the line 2, so it will increase with change in pressure drop. Maybe it is good enough to supply air fuel or fuel air ratio during idling zone, but if the same carburetor is used to supply fuel air ratio for the cruising zone and power zone during the engine operation, then we can see the fuel air ratio that would be supplied by the carburetor is far too rich during cruising zone and power zone. So, that is unnecessary wastage of fuel. On the other hand, if we design a simple float type carburetor to supply adequate fuel air ratio during power zone, that is like straight line 3, that is the curve 3, then we can see though this particular type of carburetor is supplying adequate fuel air ratio during power zone, but that the same carburetor will supply fuel air ratio during idling zone, which is far too lean from the required ratio. So, if a simple float type carburetor is adjusted to supply fuel air ratio during idling zone, the same carburetor would supply fuel air ratio during cruising zone and power zone, that is far too rich mixture than the required mixtures. On the other hand, if a simple float type carburetor is adjusted to supply fuel air ratio which is needed for the power zone, the same carburetor will supply fuel air ratio during idling zone, that is far too lean from the required ratio. So, what we can see that there are a few limitations with the simple float type carburetor, because simple float type carburetor cannot supply fuel air ratio as needed by the engine during its operation in 3 different zones. So, this is what is very important, and I can say these are the drawbacks of the simple flow type carburetor. So, that is what we have understood. Now, since simple flow type carburetor cannot, or simple flow type carburetor is unable to supply required fuel air ratio during 3 zones during the operation of engine in 3 distinct zones, we need to modify the carburetor design. So, if we try to summarize in today's class, we have tried to discuss about the mass flow rate of fuel in a simple flow type carburetor, and then we have discussed about the factors which are responsible for the deviation of the flow from the ideal one. That means, the real flow is not the ideal flow, and establishing the expression of the mass flow rate of fuel, we had seen that the flow rate of fuel, the ratio of the mass flow rate of fuel and mass flow rate of air is constant, and it is the function of delta P, that is pressure drop. And we had seen that a simple flow type carburetor cannot provide required fuel air ratio to the engine during its operation following 3 distinct zones, and we need to modify the design of the simple flow type carburetor. We shall discuss all these limitations alongside the modifications which are needed for the design of simple flow type carburetor in the next class. Thank you.